Today I'd like to share with you some applications of lasers and laser light. In fact, these applications are so special, in fact, that they will lead to these two groups being awarded the 2018 Nobel Prize in Physics. Today I'll be talking about just one of the groups, and an idea that all has to do about using light in order to manipulate objects. The story starts like this. An American scientist has a fascination with light. And he's really fascinated with what's the power of light, or perhaps more accurately, what we call the momentum of light. Light is made up of light particles, which we call photons. And a single photon always travels at the speed of light. After all, it's a light particle, which we say is 3 × 10⁸ kilometers per second. Super fast. The speed limit of the universe. But even though we say that quote-unquote photons have no mass, that doesn't mean they don't have energy or that they don't have momentum. So when we have a photon that hits something, let's say a very tiny but reflective mirror, so this is the reflective side, when it hits it and it gets reflected back, what happens is that there is a momentum change. And we see that there's a momentum change because we know the speed of light may not have changed, but its direction did a whole 180-degree turn. And as a result, we find in order for the total momentum of the whole system, namely the photon and the mirror itself, the mirror has to have a corresponding movement in order to cancel out the movement backwards, and so it's going to start moving forward. And that change in momentum is equivalent, that of the photon and that of the mirror. And so we find that total momentum, namely the momentum of the system, is going to be conserved. Namely, the initial state and the final state are going to have the same momentum, total momentum. But what does that actually imply? Well, as we saw in the case of the tiny reflective mirror, we can also see these effects on a minuscule scale while using a tiny glass bead. Let's say, for example, once again I have, instead of these photons, however, let's say I have a laser. Laser light is coming in this way. It's most intense in this region, namely there's a lot of photons, and it's less intense by the edges. There's not as many photons that are coming towards our tiny glass bead. And so if we trace, for example, the path of one photon, it might get refracted as it goes through the glass bead, like this, for example. What we find then is that same as in the case of with the mirror, when the photon changes its direction, we find that our glass bead must have a corresponding change for the total momentum to remain conserved. In this case, we can see the total momentum is that the light particle had some velocity forward. So overall, we want the system to still have some velocity forward. So when we can do that is to offset this direction change, we can have our glass bead move in a different direction. And so we can see that roughly the overall net momentum is still going to be going forward, the same as it was before. Now you might think, okay, then maybe the glass bead starts moving slightly upward in a diagonal fashion. But since it's a laser, we find that there's another particle on the other side that's doing exactly symmetrically the same kind of effect. And so ultimately these effects are going to cancel out. And what's surprising is that we can actually see that there's some kind of net attraction to the center of the beam for the glass bead, namely the part where the light is most intense. And we can see that because there are going to be the most photons that are passing through this most intense center region. And as a result, they're going to scatter away from the center, thus causing the glass bead to want to stay in the center. So we can almost treat it as if there's a net attraction of the glass bead to the most intense part of the beam, namely the intense part of the laser. Now the implications for this are actually pretty momentous. For one thing, what we can do is if we can say that, okay, we have our laser light, most intense in the middle, less intense on the sides, and we're shining it on this glass bead. Now, what happens if we try shifting our whole laser up or down a little bit? We can find that the glass bead actually also gets attracted up or down following the laser light, because once again we have that net attraction, which really results from the interaction of all of these tiny photons, all of these tiny light particles, and their momentum changes while compared to the comparatively big glass bead. Now, an even more interesting thing is that what if we don't want our glass bead to have a momentum forward in order to keep the total momentum conserved? Well, what we can actually do is try focusing our laser. And for example, let's say I have our laser again, but instead of just directly shining it on the glass bead as we have here, I now put a focusing lens in front of it. So as a result, the laser focuses to some kind of focus point, where the focus point is really going to be the place where the laser light is most intense. All of the light particles are squeezing through this space, and then they're moving on forward. What we find then is that if we continue following this idea of net attraction, we find the glass bead is actually going to be attracted right to this area, slightly past the focus. And we can see here that it also makes sense because all of these light particles are passing through. Most of them are passing through, once again, the center line, or where the focus is. But this time, since the most dense area of the laser is where the focus is, the glass bead actually doesn't get pushed out as far. It still gets pushed out a little bit by the total momentum, but it still ultimately gets attracted to where the focus point is. And so it makes a compromise ultimately by staying in this region where it's pretty much just stuck there. And we can then manipulate it. So if we move it up, if we move our laser light down, we find that our glass bead is just going to corresponding follow up or down. And so that really allows us to manipulate these tiny glass beads. But what's the use of really manipulating these glass beads in the first place? So really what these focus lasers allow us to do is that while we can manipulate these glass beads, that really allows us to be able to look inside our human living cells and learn more about the molecules, the biological molecules that are inside them. So for example, such as the kinesis molecule, which might be walking along the extracellular matrix of a cell, for example. And what's really amazing about this is that what we're able to do is that when we use this apparatus and use it in the cell, instead of previously we can only deal with dead cells since we would be afraid of damaging it, since this is just really made of light and a lens which we don't have to put inside of it. But all of the rest is just light. What we can do is attach light, and then we can be able to, for example, manipulate this kinesis molecule right here, and we'll be able to measure how many steps it takes. We'll be able to really delve deeper into the living cell without worrying about causing damage to it, because we're using these small amounts of light, and they're very focused and they're very manipulative, and we're able to move these molecules around. And so due to their precision, and really due to the idea of how we're able to use them, these focused light beams are called optical tweezers. We're able to manipulate these biological molecules so precisely, such as if they were tweezers. But in reality, they're actually tweezers, but they're made of light.